Gases, Part 5, Molar Volume and Gas Stoichiometry. In this video, you'll predict the amounts or volumes of gaseous reactants and products in a chemical reaction. Let's get to it. Did you realize that the ideal gas law shows us that equal volumes of gases at the same temperature and pressure would contain equal number of particles? In fact, it doesn't even have to be a pure substance. It could be a mixture of gases even. So the same size container at the same temperature and pressure, if it's CO2 or H2 or O2 or air, no matter what, it will be the same number of particles. And you don't even have to count them, which is good because you can't. Instead, we can use the mathematical relationships to calculate the quantities. Do you realize what this means? Do you realize what we can do with this information? It means we can do stoichiometry. But first, we'll look at a convenient dimensional analysis conversion factor shortcut that comes out of the ideal gas law. It is molar volume, sort of like molar mass, but for the volume of a gas. At standard temperature and pressure, known as STP for short, the volume of 1 mole of any gas is 22.4 liters. This conversion factor can be used to convert between moles and volume of gas at STP. 1 mole of any gas is equal to 22.4 liters of gas at STP. Let's try using molar volume here. What mass of ammonia gas will occupy a volume of 2 liters at standard temperature and pressure? Go ahead and pause the video, grab a periodic table and a calculator, and let's see what you can come up with. I made a little map of what we're going to need to do. We need to convert the liters of NH3 into moles of NH3, and then into grams of NH3. To do this, I'll use the molar volume, 1 mole NH3 over 22.4 liters of NH3, to convert 2 liters into moles of NH3. Then I'll use the molar mass, 17.04 grams NH3 over 1 mole NH3, to convert the moles of NH3 into grams of NH3. Running the numbers shows 1.52 grams of NH3. Now we have two ways that we can get moles of gas from things like pressure, volume, and temperature. We can always use the ideal gas law solved for N, PV over RT. But when the gas is at STP, we can also use the molar volume relationship. 1 mole is equal to 22.4 liters. Now we can do some stoichiometry to investigate the quantitative relationships between the amounts of reactants and products. Here's a stoichiometry problem. Ammonia gas is synthesized from hydrogen and nitrogen in the Haber process. If excess H2 reacts completely with 1.15 liters of N2 at a pressure of 3.00 atmospheres and a temperature of 298 Kelvin, what mass of NH3 can be produced? Pause now and solve the problem, but don't forget you'll need a balanced equation because it's a stoichiometry problem. For this reaction, we'll end up with this balanced equation. 1 mole N2 plus 3 moles H2 yield 2 moles NH3. So ultimately, we'll need to convert the liters of N2 into moles of N2, which will convert into moles of NH3 and then into grams of NH3. For now, let's use the ideal gas law solved for N to convert the volume of N2 gas into moles. We'll need to take 3 atmospheres times 1.15 liters divided by 0.0821 liter atmosphere per mole Kelvin and 298 Kelvin to get 0.141 moles of nitrogen gas. Then we'll do some dimensional analysis to finish the problem. We'll take the 0.141 moles of N2 from the previous calculation and convert it into moles NH3 using the stoichiometric coefficients from the balanced equation. We'll then use the molar mass of ammonia to convert the moles of NH3 into grams of NH3. Ultimately, we'll discover that we'll be able to produce 4.81 grams of ammonia from this volume of nitrogen gas at this pressure and temperature. Awesome sauce. Here's another gas stoichiometry problem. Lighters use butane fuel to provide a portable ignition source by combustion. What volume of butane gas at STP are burned to produce 0.350 grams of carbon dioxide gas. Pause now to solve this one. So here's the balanced combustion reaction. We've got 2 moles of C4H10 reacting with 13 moles of O2 to give us 8 moles of CO2 and 10 moles of H2O. Now we can do some stoichiometry. We were given the mass of CO2, which we'll need to use its molar mass to convert it into moles of CO2. Then we'll use the coefficients from the balanced equation to convert the moles of CO2 into moles of butane, C4H10. After that, since the gas is at STP, we'll use the molar volume at STP to convert the moles of butane into a volume of butane. After doing the dimensional analysis, we'll discover the volume of butane is 0.0445 liters. If you don't remember that 22.4 liters of butane is equal to 1 mole of butane at STP, then you also could have used the ideal gas law instead. V would be the unknown, and N would be the result from the first two-dimensional analysis conversion factors shown here. Thanks for watching this video on predicting the amounts or volumes of gaseous reactants and products in a chemical reaction. It's been real.